On this section 2.2, we're going to cover a little bit more on functions and their graphs. So there's going to be a couple of more items that we're going to add to what has been already covered from section 2.1. Now the first item is going to be when a function is increasing, decreasing, or constant. Now these are the three definitions that we're going to talk about. The first one states that I'm just going to create a graphical representation as we go. This one states that a function is increasing on an open interval I if f of x1 is less than f of x2 whenever x1 is less than x2 for any x1 and x2 in the interval. For example, if I'm talking about any specific interval, let's say just this interval from here to here. And in this interval we have two values of x. We're going to call those x's x1 and x2. Now what does it say about f of x? F of x means the value of y. So that this is telling me that the value of y at x1 is smaller than the value of y at x2, which is basically what is going to be shown in this picture. The value of y at x1, it's less than the value of y at x2. So I'm going to tell you in easier terms, based on the definition, what an increasing function looks like graphically. If you read the graph from left to right, if any given function is going up from left to right, then we say it is increasing. If it is going up from left to right. So this is the definition of increasing graphically. If it is rising as we move to the right. Now, second definition. The second definition states that a function is decreasing on an open interval I. So let's say my interval is from here to here again. So if f of x1 is greater than f of x2, so now it tells me that the value of y for x1 is greater than the value of y for x2 whenever x1 is less than x2. So this is telling me right here the value of y for this point, it's going to be higher than the value of y for this one. So that means that graphically a decreasing function, if we read the graph from left to right, if the graph it is decreasing or going down from left to right, then it is decreasing. So that's what does it mean by decreasing. It is going down when you read the graph from left to right. Last but not least, this is one of the concepts that we already learned on the previous section. It tells me that a function is constant on an open interval I. So let's say my open interval is from here to here. Again, if f of x1 is equal to f of x2 for any x1 and x2, meaning that the values of y for both of these is going to be the same for any x1 and x2. I'm going to say right here that the f of x1 equals to f of x2. So the values of y are the same. So the value of y at this point is the same than at this point. So what does it look like by a constant? We talked about it on the previous section. Anywhere that the function shows a horizontal graph, then it is a constant. So graphically, this is what increasing, decreasing, and constant mean and look like. Alright, so now let's go ahead and look at the first example. It says, use the graph on the right side here to determine the intervals on which the function is increasing, if any, the intervals on which the function is decreasing, if any, and the intervals on which the function is constant, if any. So, increasing means that the graph is rising from left to right. And where is the graph going up from left to right in this curve? From left to right, from left to right. We see nowhere. So that means there is no intervals where the function is increasing. Decreasing. Where in this function does this graph is going down from left to right? So we can see that at this point right here, up to here. Okay, so all of this is decreasing. However, we cannot say that this function is decreasing from -7 to -2. I know that it stops at -2, that's a fact. But it doesn't start from -7. You see that there was an arrow here, meaning that it is decreasing, 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 all over on the negative side. So that means it's going to start decreasing at -infinity, not at -7. Then it's going to stop decreasing when it reaches -2. So we're going to say that it's decreasing from -infinity to -2. Why is it that -2 doesn't carry a bracket? Because all I'm saying is that between -infinity and -2 it is decreasing. But I cannot say that it is decreasing at this point right here, because this is the middle point between the decreasing and the constant. So that point, nothing happens at the end point. Only between any two given values, that's when it is decreasing, increasing, or constant. But at one endpoint, nothing happens. So that's the reason the endpoints are not included for this matter. Now, for the last one, we need to determine the intervals for which the function is constant. And we can see that the function is horizontal anywhere after -2. And because of the arrow, it tells me that it doesn't stop being constant at 3. It continues being constant all the way to positive infinity. So starting from -2, it starts being constant after -2 and all the way to positive infinity. Now, the next definition we're going to cover is the definition of relative minimum and relative maximum. Now, on this one, basically, I'm just going to give you a simple version of this. So, if I'm given a function, any given function, so I'm just going to create a graph of a function here. Let's say this is my function. So, according to the definition, it says a function value f of a. A function value means the y value when x is equal to some number a. Is a relative maximum of f if there exists an open interval containing a. So I'm just going to say an open interval. Let's say from here to here. Just one open interval. Just going to say this open interval here. From this value to this value. I'm just going to say. So it is a relative maximum if there exists an open interval containing a such that the value of y at that a, it is bigger than any other value of y on that interval. So basically that's going to happen, as you can see on the graph. Let's say that this is a right here. And so that means that this value right here, it's going to be f of a. So what do we know about this one? This point right here. That this point has the highest value of y from all the values of y on this interval, on this little region right here. So that means that this is a relative maximum of the graph. So there is another one that we can find here. Okay. Now, if you look at this other piece of the graph right here, that's another open interval. So I'm going to say from this number to this number. So I'm just going to say this one is c. I'm just going to say the number c. And what do you notice right here? That f of c, which is the value of y when x is equal to c, right here, this number or this value is the highest value of y from all the values of y on this region. So that means in this case that these two are relative maximums. Okay, so what's going to happen? So how can we determine where we can find a relative maximum? We can say it in two different ways. where we see the peak, the top peak of a graph. So that's going to be a relative maximum, anywhere that we have a top peak of a graph. Now, not only that, we can say it in a different way. Anywhere that the function changes from increasing to decreasing, the point where the graph changes from increasing to decreasing, that is where we find a relative maximum. You can also see it here. It was increasing right here, but then afterwards it was decreasing. So at the point where the graph changes its direction from increasing to decreasing, that's where we find the relative maximums. On the other hand, where do we find the relative minimums? Anywhere that the function, any point where the function changes from decreasing back to increasing, at that point of change, that is called a relative minimum. So anywhere that the graph, any graph of a function curves down, so the lowest point of that little curve is going to be a relative minimum. And those are the definitions of what we call relative maximum and relative minimum. Now, let's work on the next problem. It says, find the numbers at which f has a relative maximum, and what is the relative maximum, and then find the numbers at which f has a relative minimum, and what is the relative minimum. So what we can see is that the graph is changing from increasing back to decreasing exactly at this point. So that's basically the highest point on this little region, on this interval. So that means that this point right here, it is a relative maximum. So that point right here is a relative maximum. So what we need to do is we need to answer two simple questions. The questions are, find the numbers at which f has a relative maximum. So basically it's asking for find the values of x where the maximum occurs. So the maximum occurs at x equals -1. So we're going to say at x equals -1, comma, the maximum is, and now the maximum means the y value. The y value for this maximum is a 3. At x equals to -1, the maximum is 3. Now, for the second question, we're going to kind of answer the same thing. Now we're going to find the relative minimum. For this one, the relative minimum happens anywhere that the graph curves down, or we can just think about it this way, where the graph changes from decreasing back to increasing. It happens in two places, here and here. So at this point and also at this point. That's exactly where the graph is changing its direction from decreasing back to increasing. So those are my relative minimums. So we're going to say, once again, at which number does it happen? So we're going to say that at x equals -2 and 0, or -2 and 0, comma, the relative minimum is -1. So at x equals to -2, which is here, and at x equals to 0, which is here, the relative minimum for both of them is -1. That's the value of y. So we have a couple of more definitions to cover in this section. Now we're going to do the definition of even and odd functions. So the first one tells me the function f is an even function if f of -x equals to f of x for all x in the domain of f. The right side of the equation of an even function does not change if x is replaced with a -x. That's basically what this statement tells me. So in order for me to determine that a function is even, I need to replace every x in the function with a -x. So we talked about this -x on the previous section when we were evaluating. So we're going to do that again. So that's basically how we determine if a function is even or odd. So if we replace x with a -x and the function gives me the same equation back, the same function back, the original function. So that means that the function is even. In other words, if I replace the negative x and the function does not change at all, then it is an even function. Second of all, if I replace, and a function is an odd function, if I replace a negative x for every x and the function changes all of the signs, then it is going to be called an odd function. So once again, if I replace every x with a negative x and the function changes all of the signs, then the function is going to be an odd function. Let's take a close look to this problem. Determine if the function is even, odd, or neither. So to determine that, we are going to substitute every x in this function with a negative x. So if I do that, then negative x raised to the 7th power means you're going to multiply negative x times negative x times negative x up to 7 times. Now let me give you an easier idea. Anytime you raise a negative to an even power, it is always going to become a positive number. To the 2nd power becomes positive, to the 4th power, to the 6th, and so on. Anytime I raise a negative to an odd power, it is going to stay as a negative. Like negative times negative times negative is still negative, and so on. It happens for any odd power. So in this case, because of the 7th power, that negative is going to stay as negative x to the 7th. Now, because of the because of the 3rd power, that negative x is going to stay as negative. So it would be negative x cubed. What we can determine, what we can find out by comparing this function to the original function is this: that all of the signs of the function were changed. Okay? If all of the signs change on the function, that means that f of x is an odd function. So if I replace every x with a negative x, then f of x is an odd function if it changes all of the signs. So now let's take a look to the next thing. Now we can also view it in a different way. A more abstract way would be this, so that you can see this. So what do you notice on the right side? That you have two negatives. So something I showed you in the first section of the semester is that we can factor that negative. So what happens if I factor that negative? What am I going to left with inside? A positive x to the 7th and a positive x cubed. Right? But what does the x to the 7th plus x cubed equals to? F of x. So this is the same thing as negative f of x. So, and I want you to compare this to the actual definition. F of negative x equals to negative f of x. And if you look at the definition, if f of negative x equals negative f of x, that is the abstract way of looking at it. That means that it is an odd function. So if I factor a negative, whenever I substitute a negative x, this is the way we can look at it abstractly. If I factor a negative and the function that I get inside is the same as the original function, then that is an odd function. That's because that's going to be the same as negative f of x, which is what the definition of an odd function says. Okay. Now I'm gonna show you the next one also in both ways. Determine if the function is even, odd, or neither. So once again, we need to replace every x with a negative x on these functions. It would be 1/2 times negative x raised to the 12th power minus 2 times negative x raised to the 2nd power. So when I raise that negative x to the 12th power, it's going to become a positive. So this is what we're going to get in this one. So it would be negative x to the 12th is going to be positive x to the 12th. That's what this gives us. But then times 1/2 is going to be positive 1/2 x to the 12th. Now, if I raise a negative x to the 2nd, that's going to become a positive x to the 2nd. But then times negative 2, it becomes negative 2x to the 2nd. Now, on this one, you see that f of negative x, well, first of all, let's look at it one way. The equation stayed the same. When the equation stays the same, that means that f of x is an even function. This is what the solution for this one is going to be. This function is an even function. Now we can look at it differently. What do you notice about this function? This function is basically this function, which is f of x. So what did we get? F of negative x equals to f of x. And if we look at the actual definition of f of negative x equals to f of x, when that happens, that means that this is an even function. Okay. So those are the two different ways. If you want to look at it concretely or abstractly, these are the two different ways of looking at the definition. Now, let's go into the next and last concept. It is going to be even functions and odd functions as symmetries. Now, if I were to graph an even function is going to be a reflection over the y-axis. So if I graph the even function, it's going to reflect to itself over the y-axis. For example, if I give you the function f of x equals to x squared. So what happens if I replace every x with a negative x right here? What is that going to give me? It's going to give me the same equation back, which is x squared. So it gives me the same thing, right? So when that happens, that's an even function. And what happens if I graph the x squared? The x squared, we talked about it, it has the shape of a U. And if you put a little dotted line of reflection right here, so I'm going to put a little dotted line on the y-axis. What do we notice? That the left side of the graph of this U, it's going to be reflected to the right side of the graph of this U. That's what creates an even function. An even function is a function that reflects over the y-axis. That is, in other words, that it has what is called y-axis symmetry. On the other hand, an odd function, that one is a function that has origin symmetry. Now I'm going to give you the main example of an odd function, which is f of x equals to x to the third power. So if I replace x with a negative x on this one, what is that going to give us? Negative x to the third power is going to change to negative x cubed. Now you see that right here the signs are opposite. So this is the same as negative f of x, which is the opposite, right? So, and what is the graph of x cubed? If we graph it, then it's going to have kind of the shape of like an S shape. Right? This is what it's going to look like. Snake shape. We talked about it on the previous lecture. Now, what does it mean by origin symmetry, so you have a better idea? Origin symmetry means that the graph is going to be reflected to itself over the y-axis, followed by a reflection over the x-axis, both of them simultaneously. So, for example, if I reflect this piece of the graph from the right side, if I reflect it over the y-axis, it is going to create this right here. But then if I reflect this piece of the graph now over the x-axis, it is going to create this that we see on the bottom. So you see that the double reflection that we created, it doesn't create something new. It creates another piece of the graph that is already there. If that happens, that means that the function is odd. When you reflect it over the y and over the x, that means origin symmetry. And if it gives me the same function back or the same graph back, then that means that it is an odd function by looking at its graph. Now, let's take a look to the last thing that we're going to do in this part, which is going to be analyzing graphs with multiple parts. So we're going to start with this. On this problem, we're going to use this graph to find the graph of the function f. This is f of x. To find all these 10 items right here. The domain, the range, the zeros, f of negative 3.5, the intervals on which f is increasing, decreasing, the values for which f of x is less than or equal to 0, any relative maxima or minima, the values of x for which f of x equals 3, and the last one is f of 0 positive or negative. These are all the questions we're going to answer for this problem. Now there is one little thing that I did not mention specifically on the previous lecture, and it was about this, zeros. And now it's time for me to talk about this. Anytime we hear the word zeros, now there are several words that are related to each other. When I'm talking about x-intercepts, this is something I want you to keep in mind. X-intercepts have several words that represent it. Zeros, roots, and solutions to an equation. When I'm finding the zeros, the roots, or the solutions to an equation, we are finding basically the x-intercepts. Okay. Now, for zeros, we're talking about real zeros. For roots, we're also talking about real roots, and solutions, real solutions, because the intercepts are real answers on which the graph of a function crosses the x-axis. So they must be real zeros, real roots, and real solutions. Okay. So that's exactly what the zeros basically is asking. If there's anywhere that the graph crosses the x-axis, that's what the zeros means. In other words, zero is another word for the value of x for which the function value is equal to 0, or the y value is equal to 0. Okay. So let's go ahead and answer the first question, which is the domain. On this function, we see that this graph keeps on going to the left side. So what does that mean? That means that -6 is not the smallest value of x. -7 is not the smallest value of x. It's not -8, not -9. So this graph is going to have all of the negative values of x in its graph. So it's going to go all the way to -infinity, because it contains all the negative values of x in it on the bottom. Now, what is the largest value of x that this graph contains? It is +2, and it includes the +2 because it has a closed circle. It has a point. That point means that the 2 is included. So the domain of this function is going to be anything from -infinity to +2, including the +2. So from here to here, that's where we see all of the points on the graph. All of the points are located anywhere from -infinity to that number, which is +2. We see that all the points are in that region. Next, now we're going to find the range of this function. I'm going to do it right here. That's letter B. For the range. Now, if we look at this graph, the -6 is not the smallest value of y, because this graph is going to keep on going this way. Okay, what does it mean? That -7, it also has a point at -7, it also has a point at -8, it also has a point at -20, it has a point at -100, it has a point at -1000, and so on, and so on, and so on. So what is the smallest value of y that we're going to find on this graph? -infinity. There is none, because it keeps on going all the way down. Now, what is the highest value of y that we can find on this graph? The highest one, it's going to be up to here, because there is nothing after that number. So the highest is going to be 3, and it passes through 3, so it is including the number 3. So when we write the range, we're going to say that the range is anything from -infinity, which is from the smallest, comma, all the way to the largest, which is +3, including +3. That would be the range of this function. Now, the next problem, now we're going to find the zeros right here. Now, I mentioned to you what the word zeros means. Zeros means the points where the graph crosses the x-axis. In this case, those will be this number and this number. So the zeros will be x equals to -4, comma, and +2. Or we can write them as ordered pairs. It would be -4, comma, 0, and 2, comma, 0. Those will be the 2 points. We can write them either like this or like this as ordered pairs. Letter D. Now letter D is asking us to find f of negative 3.5. So let's go to this graph right here. Letter D, we're going to find f of negative 3.5. We talked about this before on the previous section. What does this mean? That we're looking for the value of y when x is equal to negative 3.5. So we're going to go to negative 3.5 on the x-axis, which is right in here. And what we need to do is locate the point on the graph and find the value of y at that point. So the point on the graph is going to be right here when x is negative 3.5. And the value of y at this point is going to be positive 1. So we can say that f of negative 3.5 it equals to positive 1. That's the value of y at this point. Next one. Now we're going to find letter E. Letter E says the intervals on which the function is increasing. So we need to find out from where to where is this function increasing, meaning that the function is going up from left to right. So we see that it is always increasing at this little region. But the question is, where does it stop increasing right here? Once it reaches this point right here, which is negative 1. Now, can I say that it starts increasing at negative 6? No, because it is increasing also from negative 7. It is increasing also starting from negative 8. In fact, since this keeps on going, we can say that it is always increasing starting from negative infinity. And it stops increasing once it reaches negative 1. So it is increasing on this little region. So we're going to say from negative infinity all the way to negative 1. It is increasing. Next one. Now we want to find out the intervals on which the function is decreasing. I believe this is f. Yes. So from where to where is the graph decreasing, meaning that it is going down from left to right. It is starting to go down right after negative 1 right here. So it is starting to go down. And where does it stop going down? Once it reaches this number, which is positive 2. So between negative 1 and positive 2, the graph of this function is decreasing, which means it is going down from negative 1 all the way to positive 2. Is this function constant anywhere? No. But we're not being asked for constant. So let's go to the next question. After f, we have g, which is the values for which f of x is less than or equal to 0. So g, I'm going to put the values for which f of x is less than or equal to 0. Now, what does it mean? First of all, let's think about this. What does it mean by the values of x for which f of x is equal to 0? That means the values of x for which y is equal to 0. So y is equal to 0 or f of x is equal to 0 is going to happen right here, and it's going to happen right here. So we can automatically say that one of the solutions is the number 2 itself and the number negative for themselves, by themselves, right? But now those are the values for which f of x is equal to 0. Now the question here is, what does it mean by the values for which f of x is less than 0? That would be the next idea. Less than 0 means for which the y values are negative. This is where f of x is less than 0. On the bottom. So, and you can see that on this portion of the graph. So can I say that the graph right here, it is less than 0 from starting at negative 6? No, it is also less than 0 at negative 7. And also we can say that it is less than 0 at -8. We can also say that it is less than 0 at -9. Now, it is always negative anywhere before -4. So we're going to say, starting from -infinity, it is less than 0. So we're going to say from -infinity all the way to -4. And what do we know about -4? At -4 is exactly equals to 0, and we have included that in here. So that means that we need to include the -4. Okay? But there's another solution for which it is also equals to 0, and that solution is at +2. So that is just one single number, so when it is just one number, we can write it in a set. Now, to say, this is something very important that you have to learn, to say that the values of x for which f of x is less than or equal to 0, it's anywhere from -infinity to -4, or at 2, we can say the word or using a mathematical symbol called union. It is represented with the U. And that union stands for the word or. So that means that this function is less than or equal to 0 from -infinity to -4 or at 2. We always use the union to unite or combine several intervals together. Even for domain and range, we're going to use the union when the domain and the range consist of more than one interval. Now, let's go to letter H. Letter H states any relative maxima or minima. What do we know about this one right here? Is there a maxima or minima on this question? There is only a maximum, because right at this point it changes from increasing back to decreasing. So there is a maximum right at the point where that happens, which is right here at -1. But the question here, is it asking for y or for x? What coordinate am I looking for? It's asking for the relative maximum. The relative maximum is asking for the value of y. So my relative maximum right here occurs at y equals to 3. This is my relative maximum. So we're going to say that the relative maximum is 3, or y equals to 3. Now, look at the next question. After that, now we are looking for the values of x for which f of x is equal to 3. The values of x for which f of x is equal to 3. So that's I believe so. Yes. The values of x for which f of x is equal to 3. What does it mean by f of x is equal to 3? Meaning that when y is equal to 3. So when y is equal to 3 right here, if we go to the point, this is the point when y is equal to 3. What is the value of x when that happens? At x equals to -1. So the answer for this is x equals to -1. So y is equal to 3 when x is -1. Next, and the last question of this graph. We're going to answer the following question, which is J. Is f of 0 positive or negative? So J, is f of 0 positive or negative? What does it mean by f of 0? It means the value of y when x is equal to 0. So when x is equal to 0, it is right here. And we need to locate the point. So when x is equal to 0, this is my value of y. Is this value of y is positive or negative. That's exactly what the question is asking there. And we can say that it is positive. Right? So the answer right here is that it is a positive answer. So that concludes this part of the section. Now we are going to work on one more concept on this section, and that will be the last part of it. Let's go to piecewise functions. A piecewise function, it is a function that consists of two or more pieces of different graphs. That's what basically a piecewise function is going to be. A function that consists of two or more pieces of different graphs. Now, the first thing we're going to start doing right here is that we're going to evaluate piecewise functions. So this question states, evaluate the piecewise functions at the piecewise function at the given values of the independent variable, which means at the given values of x. So we're going to find three function values. The first function value states that we're going to find f of -3, which means the value of y when x is -3. Remember that in order for me to find a function value, I need to substitute that value of x into the function. But keep in mind that this function consists of two different pieces of different graphs. One of the pieces of the function is 2x plus 5, and the other piece is 2x plus 6. Now, let's be careful on when we evaluate, because when we talk about pieces, that means that this piece of the graph consists of several values of x, and this piece of the graph consists of other values of x. So each one has its own set of values. So the first one, you see that the first graph, 2x plus 5, consists of, this is a line, as we have done it before. This is just a regular line, but this line only consists of any value of x that is less than 0. This is the domain of those graphs right here. So you always need to look at the domain. So as we can see, based on what this tells us, that the first graph consists of any value of x that is less than 0. So if I were to graph this function, this piece of the function only contains the negative values of x in the graph. So if I ask you this, which one of these two pieces of the graph contains x is equal to -3 in its domain? The first graph or the second graph? In this case, it would be the first one, because -3, it is in the domain of the first one. It is less than 0. So then, if I want to find the value, then we're going to go to the first piece of the function, which is f of x equals 2x plus 5. -3 is contained in this function. So if I want to find the function value at x equals -3, then we're going to replace -3 into the x, and that is going to give us the function value when x is -3. So f of -3 equals -6 plus 5. So f of -3 equals -1. So when x is equal to -3, y is equal to -1. Next one. Now we're going to find the second function value. It is f of 0. So we want to find the value of y when x is equal to 0. Now the question is, which one of these two pieces of the function contains the value x equals to 0 in its domain? That would be the second function, because the second function has the equal to 0, meaning that this one includes the x equals to 0 in its domain. So if I want to find f of 0, we're going to use the second function, f of x equals to 2x plus 6. And if I want to find the value, we need to replace x with a 0. So it would be 2 times 0 plus 6. So we're going to get f of 0, it's going to be 0 plus 6, which is going to be a 6. So that means that on this piecewise function, when x is equal to 0, y is equal to 6. And the last one right here, we're going to find f of 3. So we're going to find the y value when x is equal to 3. Now, which one of these two pieces of the function contains x equals to 3 in its domain? That would be the second piece, because this one contains all the values of x that are greater than 0, and that is greater than 0. So in order for me to find that function value, we need to use the second piece of the function, which is 2x plus 6. So we're going to replace x with the 3 on this function to find the function value. So we're going to get f of 3 is going to be equal to 2 times 3, which is 6 plus 6. So f of 3 equals to 12. Meaning that when x is equal to 3, y is going to be equals to 12. And this is how we evaluate our piecewise function. The last part of the section that we're going to cover here is going to be graphing piecewise functions. So we're going to graph two of them right here. First one. He tells me in this problem that the domain of the piecewise function is negative infinity to positive infinity. So when we connect these two pieces of the graph, you will see that it's going to contain all of the values of x in the graph all together. That's what it's saying right here. What we want to do is we want to graph the function and then use the graph to determine the domain, not the domain, but the range of this function. So to graph each one of these pieces, I'm just going to separate it into two. Okay, so I'm going to say f of x equals to negative 2x. I'm just going to graph that one by itself, and I'm just going to graph this one by itself. F of x equals to negative 6. So the easiest way to do this is that we're going to create just a little table for this. And what do we know about f of x equals negative 2x? That this function contains any value of x as long as it's less than or equals to 0. So it's going to contain the values of 0, negative 1, negative 2, negative 3, negative 4, negative 5, and so on and so on and so on. So it's going to contain all the negative values of x that are negative on the left side. So how do we find the value of y? We're going to replace the values of x that we picked according to what that function domain told us. We're going to replace it into the function f of x equals negative 2x. So we had negative 2 times x, which is 0, gives us a 0. Negative 2 times x, which is negative 1, gives us a 2. Negative 2 times x, which is negative 2, gives us a 4. And negative 2 times x, which is negative 3, it gives us a 6. So we see that the points for this piece of the graph are going to be 0, 0, negative 1, 2, then negative 2, 3, negative 2, 4, and negative 3, 6. So I'm going to make this a little bit larger right here so we can see the graph more detailed. So for that first piece we have 0, 0. That's one of the points on this line. Then negative 1, 2. Then negative 2, 4. And then negative 3, 6. And it continues to the left side as we taught. So that means that this graph is going to keep on going from 0 to all the numbers less than 0. So in other words, all the numbers to the left side of it. So it just keeps on going to the left. We don't need the right side of this line because this one only contains the numbers which are less than or equal to 0 in the domain. Now, next and last piece of the graph. Now we are going to be graphing the function f of x equals negative 6. Now the question is, we already talked about when it's a constant. That constant is represented by a horizontal line. But where is that horizontal line is going to be? Only for all the values of x which are greater than 0. So we're going to have a horizontal line at negative 6. So negative 6 meaning down here. For all the values of y which are greater than 0. So exactly right here. But for the values of y greater than 0 means it is going to be a horizontal line anywhere after negative 6. Now just keep in mind, and anywhere after 0, just keep in mind that just because it says greater than 0, that doesn't mean we have to start from 1. Because 0.5 is greater than 0, 0.4 is greater than 0, 0.3 is greater than 0. You still have to start from the 0 right here, but since that graph, the second equation, does not contain the value 0, then all you're going to do is this. You're going to create an open circle at 0. That open circle means that it is not included in this graph. 0 is not included in the graph of this function, and you see that on the other one I created a closed circle right here. That means that the 0 right here, it is included, and it is included because it has the equal to 0, so that means that it includes the 0 on this graph. So those are the two pieces of the function, and if you connect them, you see that both of them contain all the values from negative infinity all the way to positive infinity. Now, what about the range? That's what the second question on this function is going to be. What is the range? The range, it is going to consist of, first of all, this y value right here, negative 6. You see that this one is always negative 6, right? So we're going to put the negative 6 alone, but that's not the only range. Or we can also say that the range is anywhere from here, which is from 0, and it keeps going up, because this arrow tells me that it just keeps going up all the way to positive infinity. So we can say that the range is negative 6 to negative 6 by itself, or from this number 0 right here all the way to positive infinity. And that is the range of this function. So we're going to create one more piecewise function right here. The next piecewise function we're going to do is this one. So this problem states the domain of this function, again, when graphed, is going to be from negative infinity to positive infinity. The question here is that we want to graph the function, and also we want to find the range of this function again. Alright, so let's go ahead and create the sketch. First thing is that we need to graph each one of those functions separately. So I'm going to create a table for the first piece of the function, which is f of x equals to 1/2 x squared. And I'm going to create a table for the other piece of the function, which is f of x equals to 3x minus 1. Now, what values does the first function include? According to the domain. The domain tells me that it includes any value as long as it's less than 1. That doesn't mean that we have to start from 0, remember, because anything less than 1 would be 0.9, 0.99, 0.98, 0.97. So we're still going to start from 1, but in the graph we're going to say that 1 is not included. Keep that in mind. We're going to say that this point is not included. So I'm going to write that once I evaluate it. Okay. So, and then it's going to be anything less than 1, which is 0, negative 1, negative 2, negative 3, and so on, and so on, and so on. So I'm going to do all the way to my 5 points that I usually do. So I'm going to put also the negative 3. So, right here, I need to substitute them. So, 1/2, that is my function. Let me make this a little bit less bold. This is 1/2 times x, which is 1 squared. 1 squared is 1 times 1/2 is going to give me a 0.5. Now, 1/2 times x, which is 0 squared. 0 squared is 0 times 1/2 is still 0. Now, 1/2 times negative 1 squared. Negative 1 squared is 1 times 1/2 is going to give me 1/2, which is 0.5. And 1/2 times negative 2 squared. Negative 2 squared is 4 times 1/2 is going to give me a 2. And the last one here is 1/2 times negative 3 squared. Negative 3 squared is 9 times 1/2, it's going to be 4.5. So when we graph these points, we're going to get, remember that the first one, 1 is not included because 1 is not part of the graph of this function. We already said that at the beginning because it includes the numbers greater than 1 only, not equal to 1. So at 1 comma 0.5, so 1 comma 0.5 right here, we're going to draw an open circle, meaning that this point is not included. Then 0, 0. Then negative 1 and 0.5. then negative 2 and 2, that's another one here, then negative 3 and 4.5, and it keeps on going. Remember that the shape of x squared, it creates a parabola. So when I connect these points, it's going to create a parabola, but only that appears on the left side all the way until it reaches the positive 1 and it stops. So this is what the parabola is going to look like, just this piece of the graph right here. We don't need the right side, right, because it has to stop before getting to 1. Now, the next piece of the graph, now we're going to graph the function f of x equals 3x minus 1. So we're going to create a table for this again. And what values does this function include? It includes any number as long as it is greater than or equal to 1, meaning that it's going to start from 1 and it includes the 1 right here. So I'm going to say right here it is included. Okay? And it's going to be a 2, it's going to be a 3, it's going to be a 4, and so on, and so on, and so on. So I'm just going to do a few values. Remember that for a line we only require 2 points. So but I'm just going to do those 4. 3 times 1 minus 1, that's going to give me a 2. 3 times 2, which is 6, minus 1, that's going to give me a 5. 3 times 3, which is 9, minus 1, it's going to give me an 8. And 3 times 4, which is 12, minus 1, it's going to be an 11. So let's connect those points right here. So when x is equal to 1, y is equal to 2. So it's going to include it. Then when x is equal to 2, y is equal to 5 right here, and it's going to include it. When x is equal to 3, y is equal to 8, and it's going to include it, and so on, and so on, and so on. So this graph is going to be represented by a line that starts at 1, and it keeps on going to the right side. So it keeps on going. Last question. We need to answer for letter B. We need to determine what the range of this function is. Now, if we look at this function, what is the lowest value of y in this function? 0, because it starts right here at 0. Now, does it ever stop as it goes up? No, there is a little gap right here, but that little gap, that doesn't mean that these values are not in the range, because you see those values are in this little piece. Even though they are not in this piece right here in between, they are contained in this graph. So this graph doesn't stop. So we can see that this graph, the lowest value of y is 0, and the highest value of y, since it keeps on going up, it is going to be positive infinity, including 0, of course. Bracket at 0, comma, all the way to positive infinity. And now this section is complete. So section 2.2 on more functions on the graph, on functions and their graphs.